In this screencast, we're going to discuss vectors and scalars, particularly vector addition, how we add vectors, from the perspective of physics. I know that in HL mathematics you treat them much more sophisticated manner, but I want to show you the conventions and practices that we see in physics. First, let us consider this diagram, which shows vector addition. We have a vector A and a vector B, and we add them. We go to the very beginning of the first one to draw the first vector. At the end of the first vector, we draw the second vector. We call this head to tail, head of the arrow to the tail of the next one. Then, to find the sum of the vectors when we add them, A plus B, we go to the very first vector and draw a vector from the very beginning to the very end. And so, whereas this is vector A, this is vector B, this is vector A plus B. We have a special name for this in physics. We call it the resultant. It is what results when we add those two vectors. Now this method I just showed you is the vector addition method. What I call the vector addition method. It is the method you should always use that makes the most sense, has the widest application, and allows you to do increasingly complicated problems. However, when you look online or look in textbooks, and even when you see both Regents and IB questions, you will see that they have written questions as if you're going to use a different method called the parallelogram method, which is down here. This is not a good method, and we will see over the next few screencasts why. So here we have vector A, like so, and we have vector B. Notice instead of being drawn, vector B being drawn at the end of vector A, as it is in the vector addition, it's drawn with the same starting point, out of the same vertex. So here's A, and this is B. It's called the parallelogram method because you are asked to complete a parallelogram based on those two vectors. So what you see is this B is constructed here at the end of A, and this A is constructed at the end of B. The resultant then is the diagonal that comes out of the vertex. It's the diagonal of the parallelogram that comes out of the vertex of the two vectors. Well, if you look at this parallelogram method, in comparing these two diagrams, you can see here's vector A, and B is drawn at the end of it. Well, if you look here and see here is A, and you draw B at the end of it, it will produce this resultant. So the parallelogram, one of its disadvantages is it has more steps. More steps are required, and the drawing and construction of it is more difficult. So let us first take a look at, in the ensuing pages, I'm going to consider one-dimensional and two-dimensional motion and some different examples of how we can draw and calculate the answers. So in one dimension, we have a number line like we've seen before. So we have Max, who is located 3 meters south of the tree, so we'll say this is our tree. And so he is located here, and he walks 5 meters northward. And we even see that 1, 2, 3, 4, 5. In our pictures, it just naturally works that we would draw this as an arrow to scale. So there's a vector, 5 meters northward. Then he walks 2 meters southward. Then 4 meters northward. Then 1 meter southward. What is his final position? Well, from this picture, since we were given the initial position, we can see he's located a position of 3 meters north. So it's very easy to see. What is his displacement? Well, the displacement is defined as the change in position. So we've gone from -3 to +3, so his displacement would be 6. And drawing the resultant on here, we have an overall displacement, or the resulting displacement, is r, +6. Now, algebraically, how would we do this? We can do vectors algebraically in one dimension. So we would start out, the algebraic would be the resultant is the sum of the displacements. The blue arrow represented a displacement, the orange arrow was a displacement, green arrow was a displacement, the gray arrow was a displacement, and the resultant is a total displacement. So if we look at our first one, the first vector is delta x1, and we have a delta x2, delta x1, delta x2, delta x3, and delta x4. Displacement 1 was +5. Displacement 2 was -2 plus a -2. Displacement 3 was +4. And displacement 4 was -1. 5 and -2 is 3. Plus 4 is 7. Minus 1 is 6. So the resultant is 6. Now, if you notice in this case, what does the resultant represent? It represents the displacement. Not the position. So in this particular case, working with displacements and positions, the vectors, when we're adding and subtracting them, give us the displacement. So what do we do to find the position? Well, we know the definition of displacement is x minus xo. So the question is, where is he? X? Well, then x is delta x plus xo. And delta x we said was 6, and xo was -3, the initial position. So we have a position then of 3. Now I want us to consider this scenario starting from a different location. Let's just say we had started at -5 this time. So we have walking northward 5, then 2 meters southward, then 4 meters northward, then 1 meter southward. And we can see this is our resultant, very beginning to very end. And we can see that the displacement is +6. In both cases, the displacement is 6. So in terms of studying displacements, it doesn't really matter what the initial position is if we're only concerned with displacements. And whenever we have the displacement, we can just factor in the initial position to find the position. This is why oftentimes formulas in physics leave out initial position and don't solve for position. They work only with displacements. So that's one-dimensional vector addition. Let us now look at two-dimensional vector addition. So we have our coordinate system here, and let's label the directions. We have north, east, south, and west. And we have Max walking. We don't have an initial position, so we're dealing with displacement in this case. So we start out and with being told that he's going to walk 3 meters eastward. Now let's just say I I happen to pick this location right here, the origin, 3 meters eastward. There's 3 meters eastward. Then he walks 4 meters northward. What is his displacement? Well, his displacement is the very beginning to the very end, delta x, which is the resultant. Now, recognizing that this is 3 and this is 4, we can very easily recognize this as a 3, 4, 5 triangle. But how we would find the resultant in this case would be the Pythagorean theorem, because these are at right angles to each other. So we have a powerful tool when the vectors are at right angles to each other. Later, we will consider the cases where the vectors do not have right angles between them. But for now, we will look at those and consider them at right angles to each other. Now, so what's interesting here is that we have Max 3 meters east, then 4 meters north. What's his displacement? Well, displacement is a vector. And vectors have a magnitude, which in this case is 5 meters, and a direction. Many students think that it's okay to just say northeast. Northeast implies a perfect 45-degree angle. So we would never say northeast. We actually need to find this angle. So to find that angle, we were given the adjacent and the opposite. But we know all 3 sides. So to find the angle, we could use sine, cosine, or tangent, but it's always most prudent to use the givens. So we have in this particular case, we have our angle theta, and we have our opposite and our adjacent side. That's the hypotenuse. So we have opposite and adjacent, which is tangent. So we have tangent of theta is opposite over adjacent. Tan theta is 4 over 3. And theta is the inverse tangent of 4 over 3. And the inverse tangent of 4 over 3 happens to be 53.13 degrees. Now we would, of course, want to consider significant digits, and these numbers were given as perfect even numbers, but we want to consider significant digits here. But in any case, this is an interesting thing that a 3, 4, 5 triangle, this angle is 53 degrees. That can be useful to know that it's 53 degrees. So what we would say for our final direction is that it's 5 meters at 53 degrees north of east. And we describe it that way because if we were to create this angle, to sweep out this angle, we start pointing east and we would sweep out the angle headed northward from east. And that's about 53 degrees. So that's how we would find our resultant. 5 meters at 53 degrees north of east. Now let us consider a more complicated example where there are multiple vectors. So we have Max. We'll have him start in the same place this time. Goes 3 meters eastward. Then 4 meters northward. Then 2 meters westward. Then 3 meters northward. So we have a 3, a 4, a 2, and a 3. Of course, this one is a negative 2 because of the direction of it. So what is his displacement? We have all these little displacements, but the displacement itself is the very beginning to the very end. And we can see this is over 1 and up 1, 2, 3, 4, 5, 6, 7. So this is 1 and that's 7. Now these dimensions that make up the resultant, this 1 and this 7, are what we call the components. Whenever we have a vector at some angle, we can break it down into components or parts that are at right angles to each other, such that when we add them, we would produce the resultant. And of course, you can see this makes this very nice to resolve, because now we have the Pythagorean theorem. We can find the magnitude. So we have a squared plus b squared equals c squared, and this is a 1 squared plus 7 squared equals c squared. So c is the square root of 50, and the square root of 50 is about 7.1. And this 7.1 will give us the magnitude. 7.1 will give us the magnitude, but now we need the direction. So we've got opposite and adjacent. So we have tan theta equals opposite over adjacent. Tan theta is 7 over 1. Theta then is the inverse tangent of 7 over 1. Which is about 81.9 degrees. And you can see that's a very big angle. So if this is east and this is north, we would say 7.1, our answer would be 7.1 meters at 81.9 degrees north of east. Here's our magnitude, and here is our direction. I'd like us to go back, though, and consider consider the information we were given here before. So if we were to do this algebraically, we would need first to treat our x's. Our delta x, our displacement for x, would be the sum of the x's, the sum of the displacements in the x direction. And this, so when we look here, x in the x direction, we have plus 3. And this next vector, 4, had no x part. This one was negative 2, plus a negative 2. And this last one had no x part. So what we see then is delta x plus 3 negative 2 is plus 1. And that, of course, we see is what we end up with here, the resultant. Similarly, if we do the displacement in the y, it would be the sum of the y's, y displacements. Our first y, our first vector, had no change in the y, but this one had a change of 4. So we have plus 4 plus, this one had no change in y, and this one had a change of 3. So we have a change of 4 and a change of 3, so our displacement in the y is actually 7. And this gives us our 7 and 1 that emerged here in the drawing. So what you can see is that we can solve this kind of problem algebraically rather than by drawing, but we have both tools in this particular case. In our next example, we're going to look at cases where, where it's not, the vectors are not all perpendicular to each other. So I'm going to, because I know how this turns out, oftentimes this happens when you're doing a vector diagram, what you should do is make a sketch before to see approximately what it's going to look like. So let's start with Max down here. I'll start him away in this particular area. He's going to go 3 meters eastward. then 5 meters northeastward. Now, I haven't specified the direction here. And you'll see why shortly, but here's the first vector. And so it's 5 meters northeastward. Which I'm going to draw like that. And then we have a 10 meters northeastward. So from here, this would be east, this would be north, this would be northeast, and this would be north of northeast. So it's going to be a pretty steep angle, and it's going to be 10. Like so. So what is the overall displacement? Well, we know the displacement is the very beginning to the very end. So the overall displacement is this. But since this is on a coordinate grid, you can probably recognize that this resultant has components that drop down like this and like this. But here's where it gets interesting. If we take this vector, it's all in the x direction. So if we look at the sum of the x, the total, is going to be delta x1 plus delta x2 plus delta x3. Well, delta x1 we know is 3. It's already drawn as 3. But what about this one? Well, this is the x component here, like this. So this is x1, this is x2, delta x1, delta x2. So this is our first displacement in the x direction. This is our second, and you'll notice it's 1, 2, 3, 4. So this is plus 4. And now in this particular case, this last vector, the x component is 6. Delta x3 is 6. So 3 plus 4, 7, plus 6 is 13. So we have a change of 13. In other words, this entire, all of the x's, this whole side here is 13. Moving on to the vertical, some of the y's will be delta y1 plus the displacement in y2 plus the displacement in y3. Displacement in y1 is 0. There's no vertical, so that's 0. y2 has these components, 1, 2, 3, plus 3. And this delta y3 is 8. So that gives us 11. So the vertical is 11. What we end up with is the sum of the x's being 13, the sum of the y's being 11. So now it's a simple matter. We have a triangle like this, 11, 13. We have a right triangle. Is 13. Now this is the value in being able to break vectors into their components, because you can just add their components to make one final big triangle, algebraically. So now to resolve this in terms of the magnitude, we have a squared plus b squared equals c squared. C will equal the square root of a squared plus b squared. So c is the square root of 11 squared plus 13 squared. And C is about 17.02. So the resultant in this case is 17.02. And now, with this one being 13 and this one being 11, we can see that the angle should be about 45 degrees, a little bit less than 45, in fact. It's really important for us to estimate those ahead of time. Similarly, do with the kind of the calculation in our head to get an order of magnitude kind of estimate. And if we have two legs that are 11 and 13, we expect a hypotenuse that's greater than 13, and of course that makes sense. So now our triangle, like so, is our opposite and adjacent side, and we want this angle theta. We'll use our tangent. Tangent theta equals opposite over adjacent, and theta is the inverse tan of 13 over 11, and so theta will be actually it's 13, that's 11 over 13. So when I do 13 over 11, I got 49.8. Now, I was predicting the angle should be less than 45. So the fact that I'd made that prediction allowed me to look at this and say, wait a minute, I must have made a mistake here. And sure enough, I did. The horizontal is 13, and the vertical is 11. And that's the power of estimating the answer before you do it. And theta then is 40.2 degrees, which makes sense. So our final vector resultant would be 17.02 meters at 40.2 degrees north of east. And that's how we'd report our resultant. So that's two-dimensional vectors with components and the power of adding the components. So now let's lastly look at this two-dimensional problem using the parallelogram method. We'll have Max walk 3 meters eastward, 1, 2, 3, and then 4 meters northward, like so, and we would complete the parallelogram. Actually, this is the one that should be drawn because the two share the same end. This one should be dotted. And this is the resultant. So here is vector 3 meters. Here is the 4 meters. The shapes we draw to complete the diagram should be dotted. And the diagonal of the parallelogram coming out of the vertex of the two vectors is the resultant. And of course we would come up, notice drawing it this way, it's not quite as obvious that it's a 3, 4, 5 triangle. So how do we do the parallelogram? We draw the vectors, complete the parallelogram, and the resultant is the diagonal out of the vertex. Now I've said multiple times that this is not a good method. And it's more work, number one. Number two, it doesn't make some of the geometric relationships of the triangles as obvious. One of the other reasons is simply this. You couldn't do this problem using the parallelogram method. So with this one, we could have taken this and then drawn one over here and across here and found that the resultant of those two is a vector. But if we just add that vector and this vector, that's a problem because we're not counting them and weighting them the same. It becomes a real mess to keep track of. And in our next screencast on vector subtraction, you'll find it's a nightmare to do the parallelogram method with subtraction. So going back to the beginning, what did we cover? Two methods, vector addition, the one that you should use. I've shown you the parallelogram method. The resultant is the sum of the vectors. We have constituent vectors here, A and B. It can be expressed as A plus B. Its name is the resultant. In different situations, the resultant means different things.